For millennia, astronomy was largely blind to the majority of the universe, restricted solely to visible light. Radio astronomy broke this barrier, allowing us to detect wavelengths from millimeters to meters, fundamentally changing our understanding. Looking at this composite, we see the cool neutral hydrogen clouds in cyan and the hot synchrotron radiation from galactic jets glowing magenta. We are now truly mapping the cosmos, from vast gas reservoirs to the echoes of the Big Bang, beyond the visible spectrum. For centuries, visible light was easily scattered by cosmic dust, obscuring our true view of the Milky Way's core. The breakthrough came with radio waves. Their longer wavelengths cut through this dense interstellar matter completely. This revolution began in 1933, when Carl Jansky identified a persistent static hiss originating from the galactic center, confirming a major paradigm shift. We needed to stop just looking up and start tuning in.
Radio astronomy captures the faint cosmic hum using large dishes that collect and amplify weak signals. To truly sharpen our cosmic vision, we utilize interferometry, linking multiple telescopes to simulate a giant eye, where resolution depends only on the distance between them. While most work is passive listening, active radar mapping uses signal reflections. Intriguingly, all this data relies on the fast Fourier transform algorithm, the very same technology that now underpins your home Wi-Fi.
For decades, the Arecibo Observatory in Puerto Rico was the ultimate titan, serving as the world's largest single-aperture telescope and providing unique planetary radar capabilities to map asteroids and planet surfaces. Sadly, structural failure due to aging infrastructure led to its dramatic collapse in 2020. To ensure the Titan's discoveries remain accessible for future generations.
To truly listen to the universe, we utilize a global network of incredible instruments, often placed in remote radio quiet zones to minimize interference. Look at this map. From the VLA array in New Mexico to the massive fast sphere in China, and the SKA precursors like Meerkat in South Africa and ASCAP in Australia. We are capturing faint signals from high altitudes in Chile with ALMA, and using steerable dishes like the 100-meter Green Bank telescope to piece together a complete cosmic picture.
Back in 1964, Penzias and Wilson struggled to eliminate persistent static from their antenna. After ruling out every interference source, even pigeon droppings, they realized this persistent noise was actually the cosmic microwave background. This thermal radiation is the direct echo of creation, providing definitive evidence that the universe began 13.7 billion years ago in a hot, dense state, giving us the magnificent structure we see mapped by the Planck surveyor.
Pulsars are the ultimate cosmic lighthouses, discovered in 1967 when Jocelyn Bell noticed a perfectly repeating signal, briefly mistaken for little green men. These are rapidly spinning neutron stars, which pack the mass of our sun into a city-sized sphere, rotating with the precision of atomic clocks. This incredible regularity makes them invaluable tools. They help us test general relativity and gravity waves, and their stable pulses could even establish the framework for a universal galactic GPS system. We use the 21-centimeter hydrogen line, a faint radio emission from atomic spin flips, to penetrate the cosmic dust blocking visible light. This crucial technique allows us to map the full hidden spiral structure of the Milky Way. Importantly, when we measure the rotation of these distant gas arms, we observe them spinning far too fast based only on visible matter, creating the significant rotation curve discrepancy that serves as the primary evidence for the existence of dark matter. Fast radio bursts remain one of cosmology's biggest puzzles. We now know that some FRBs, like 121102, are not one-off events, but repeat on a predictable schedule, a periodic cycle of about 157 days, suggesting a rotational clock. Tracing the first repeating burst to a distant dwarf galaxy helped us identify the prime suspect, magnetars. These dense neutron stars possess magnetic fields strong enough to produce these incredible, brilliant blasts. Stars constantly bombard nearby exoplanets with massive flares and coronal mass ejections. A planet needs a strong magnetic field to act as a shield, preventing atmospheric stripping and enabling true habitability. When the stellar wind hits this magnetic field, it creates powerful auroras at the poles, which emit non-thermal radio waves. We use the RIMS technique to monitor thousands of stars simultaneously, helping us identify these critical magnetic shields in systems like Tau Boötes. The search for technosignatures, or SETI, looks for artificial signals that simply do not occur naturally. We specifically hunt for highly specific narrowband radio peaks, clearly distinct from the cosmic background noise floor, much like the famous 1977 WOW signal. Modern efforts such as Breakthrough Listen scan millions of stars using powerful new arrays. While a promising 2020 signal from Proxima Centauri turned out to be Earth interference, we now possess the technological tools required to rigorously validate any true signature, if it actually exists. Radio astronomy truly presents a data deluge challenge, generating petabytes of information annually. The sheer volume is staggering. EHT and SKA data rates now actually exceed global internet traffic. Processing this requires massive GPU clusters capable of managing bandwidths of 24 gigabytes per second. However, the critical risk isn't just the size. It's the fact that algorithms digest the data before humans see it, increasing a chance of missing unknown unknowns, those crucial phenomena the computer wasn't programmed to find. The biggest silent threat to observation is radio frequency interference. Everyday technology, from Wi-Fi to spark plugs, already overwhelms the faint cosmic signals we seek, and vast low Earth orbit satellite constellations threaten to blind our essential radio windows completely. To combat this, the ITU actively manages the global spectrum, while we rely heavily on protected areas, such as the 13,000 square mile National Radio Quiet Zone in West Virginia, to ensure observation silence. The future horizon promises profound discoveries, driven by two monumental projects, the Square Kilometer Array and the Next-Gen Very Large Array. SKA, the world's largest science facility spanning South Africa and Australia, will be fully operational by 2027. Complementing this, NGVLA will deliver 10 times the sensitivity of current instruments, fundamentally expanding our reach. As the saying goes, radio telescopes are rarely known for what they were built for. These instruments are designed to reveal the unknown unknowns, discoveries we haven't even hypothesized yet. Radio astronomy has fundamentally revolutionized our understanding, moving from detecting a simple telephone lab hiss to mapping the very dawn of time itself. As you can clearly see in the cumulative chart, the rate of discovery has become exponential, particularly in the last 2 decades. RA allows us to peer through the optical dust and probe the earliest, most intense and obscured phases of star, galaxy, and black hole formation, providing our primary tool for decoding the dark universe. For 57 magnificent years, the Arecibo Observatory stood as a true titan of science in Esperanza, Puerto Rico. Its massive 305-meter diameter dish, spanning over 73,000 square meters of collecting area, gave us unparalleled insight into the cosmos and Earth's ionosphere. From its founding in 1963 until its operational end in 2020, Arecibo transformed planetary radar and radio astronomy, leaving an irreplaceable legacy that continues to inform our work today. The observatory's genesis was a perfect convergence of scientific curiosity and Cold War necessity. Cornell's William Gordon needed to study the ionosphere, strategically utilizing Puerto Rico's natural limestone sinkholes to cradle the massive 1,000-foot reflector cost-effectively. Funded largely by ARPA, the resulting structure served a dual purpose. It was a premier scientific eye on the cosmos, while simultaneously acting as a crucial defense tool for analyzing atmospheric physics related to ballistic missile detection. The evolution of this instrument was marked by 2 key changes.
in 1973, replacing the original wire mesh with 38,000 adjustable aluminum panels dramatically transformed it into a high-precision radio telescope. The 1997 Gregorian upgrade then added a massive 270-ton dome to correct for spherical aberration. Crucially, supporting this immense new weight required 6 auxiliary cables, creating a structural dependency that ultimately played a critical role in the catastrophic 2020 collapse.
Arecibo was truly unique because it didn't just passively listen, it operated as an active planetary radar, an essential flashlight in the dark solar system. Its powerful 1 megawatt transmitter let us bounce signals off objects to determine precise orbits and rotation. For example, Arecibo disproved the old theory about Mercury's rotation and gave us the first detailed images of bizarre asteroid shapes, like the Dogbone 216 Cleopatra. Crucially, this capability served as our primary defense system for tracking hazardous near-Earth objects. Arecibo's immense sensitivity revolutionized radio astronomy and our understanding of the deep sky. The 1974 discovery of the first binary pulsar provided crucial indirect evidence of gravitational waves, earning the 1993 Nobel Prize. Moreover, utilizing advanced technology like the Alpha 7 beam array, the facility confirmed the existence of repeating fast radio bursts, demonstrating these high-energy extragalactic signals could survive the vast journey across the universe.
Arecibo's third scientific pillar spanned everything from the ionosphere to popular culture. Initially, it functioned as an ionospheric heater, allowing researchers to deeply study plasma physics and the Earth's gaseous envelope. But its truly defining moment was the 1974 Arecibo message, a 1,679-bit interstellar broadcast demonstrating human technological achievement. This incredible scale cemented its cultural legacy, becoming a memorable star itself in films like GoldenEye and Contact.
We can trace the beginning of the end back to Hurricane Maria in 2017, which caused a snapped feed line and punctured the dish, exposing initial structural weaknesses. The situation worsened dramatically in August 2020 when an auxiliary cable slipped, causing another major tear. The critical failure arrived just 3 months later. A main cable snapped. This moment meant the remaining structure was carrying loads far exceeding its safety factors, ultimately determining that the telescope was too unstable to repair safely.
The catastrophic failure occurred precisely at 7:55 a.m. on December 1st, 2020. Though the NSF had already decided on decommissioning due to critical safety risks, the structure failed prematurely. The core event was the second main cable on Tower 4 snapping, which unleashed the 900-ton instrument platform. The platform swung violently outward, shearing off the concrete support tower tops and crashing directly into the reflector dish below. The result was the total destruction of the instrument, but crucially, no injuries were reported during the incident. The National Academy's 2024 report isolated 3 primary factors for the failure, starting with long-term zinc creep within the spelter sockets, causing the filler to deform over 57 years and lose its grip on the steel cables. Second, a unique phenomenon called electroplasticity accelerated this creep rate, induced by high-energy electromagnetic waves from the radar transmitters. Critically, the structure also lacked sufficient redundancy. When that first cable failed, the sudden transferred load immediately exceeded the remaining capacity, leading to catastrophic failure. The telescope may be gone, but the golden copy, our 50-year history of the radio sky, survived. The immediate priority was rescuing this incredible inheritance, 3 petabytes of irreplaceable data. This archive includes the raw measurements underpinning Nobel Prize research and critical asteroid tracking logs. Our team's monumental challenge was safely migrating these original tapes and hard drives from the disaster zone to a permanent, secure cloud repository. Our key partnership for open science, uniting the Arecibo Observatory, UCF, and TAC, has secured a permanent, safe home for the entire historic data archive. This massive move places the information on TAC's ranch system.
Crucially, the archive is now fully open access, allowing researchers globally to query over 1,800 scientific proposals spanning astronomy, planetary, and atmospheric sciences, ensuring this priceless resource yields many future discoveries.
For 5 decades, astronomy has been the primary driver of our facility, accounting for 1,114 proposals, reflecting its massive dominance over other disciplines. This sustained activity has fueled significant academic impact, successfully supporting over 335 astronomy-focused PhDs alone. To handle this high volume of research, our data generation capacity is immense. The Alpha instrument is constantly working, contributing over 80 terabytes of raw observational data every single year.
While the great year is gone, the memory remains perfect. In October 2022, the NSF decided not to rebuild the telescope, instead transitioning the site into a world-class STEM education center. While we salvaged key artifacts for preservation, the real legacy lies in the 3 petabytes of scientific data secured at TAC. This massive repository ensures the Arecibo Observatory will continue producing essential scientific discoveries for decades to come, marking a truly new beginning for this historic location.
For millennia, astronomy was limited to visible light, leaving us deaf to the universe's full story. Our detective story begins accidentally in 1932, when engineer Carl Jansky built this merry-go-round antenna to track atmospheric noise. He found mysterious repeating static, the scruff on his charts. This accidental clue revealed the true, invisible cosmos, a violent, energetic universe centered around Sagittarius A star, permanently transforming how we map the galaxy. For centuries, the center of our galaxy remained an optical mystery. Interstellar dust acts as a cosmic blinder, completely obscuring the core in the visible light spectrum. The key to solving this came when we utilized the electromagnetic spectrum's radio window. These longer wavelengths cut right through the dust and atmosphere, finally revealing the spectacular high-energy structure of the galactic center that was previously hidden from our view.
Carl Jansky's assignment in 1932 was simple. Use this massive 100-foot rotating merry-go-round antenna at Bell Labs to eliminate noise disrupting transatlantic radio calls. The apparatus rotated 360 degrees every 20 minutes to meticulously pinpoint the source of static. While he successfully tracked terrestrial interference, a faint, persistent hiss remained. Jansky soon realized this residual signal originated not from Earth or the Sun, but from the center of our galaxy. He set out to kill the noise and accidentally founded radio astronomy.
Jansky rigorously classified the radio static into 3 distinct types. We successfully identified suspects 1 and 2 as local, violent thunderstorm spikes and the continuous background noise from distant atmospheric storms. Crucially, the remaining signal, suspect 3, was a persistent, faint mystery hiss that maintained a steady intensity day and night. This residual signal refused to be explained by terrestrial weather, convincing Jansky it was a steady hiss-type static of unknown origin, marking the birth of radio astronomy.
Jansky initially suspected the sun, but the data revealed a crucial mismatch. If the source was solar, the signal would have peaked exactly every 24 hours. The smoking gun was that the peak actually appeared 4 minutes earlier each day, resulting in a precise 23-hour and 56-minute cycle. This rotation matches sidereal time, the Earth's rotation relative to the fixed stars, proving definitively that the powerful radio source was not local, but galactic.
We finally tracked down the culprit, Sagittarius A. Jansky successfully correlated the mysterious peak signal directly with the densest region of the Nungiway, which you can see centered precisely at 18 hours right ascension. The verdict was published in 1933. He had definitively detected star noise from the heart of our own galaxy. This groundbreaking finding confirmed the extraterrestrial origin of the static, launching the entire field of radio astronomy.
For a decade after Jansky, Grote Reber stood as the world's sole radio astronomer, building this groundbreaking parabolic telescope himself. He initially searched for thermal heat at high frequencies, but found nothing.
His key insight came when he switched to a much lower frequency where the signal unexpectedly intensified. This crucial discovery proved the radiation was non-thermal, specifically synchrotron radiation, generated by high-energy electrons spiraling within galactic magnetic fields.
The Song of Hydrogen refers to the faint 21-centimeter radio signal emitted when a neutral hydrogen atom undergoes a fundamental spin-flip transition. Predicted in 1945, this specific 1420 MHz frequency was successfully detected 6 years later. The discovery's impact was enormous. Since hydrogen is the cosmos' most abundant element, tuning into this frequency gave us the revolutionary ability to map the spiral arms of the Milky Way, effectively seeing right through the obscuring cosmic dust.
When Penzias and Wilson began working with the Holmdel horn antenna, they were plagued by a persistent, annoying excess noise equivalent to 3.5 Kelvin. They ruled out all earthly sources, famously even scrubbing the antenna clean of pigeon droppings. They finally realized the noise was perfectly isotropic, the same in every direction. This unkillable hiss wasn't interference, it was the cosmic microwave background, the cooling afterglow of the Big Bang itself.
In 1967, grad student Jocelyn Bell Burnell analyzed 100 feet of chart data daily when she spotted this tiny bit of scruff. The resulting anomaly was a radio pulse repeating with extreme precision every 1.33 seconds. Given the seemingly artificial rhythm, they nicknamed it LGM1, Little Green Men. We now know these are pulsars, revealing that the universe itself holds clocks far more precise than anything we possess on Earth.
Pulsars are truly the cosmic lighthouses of the universe. The mechanism involves a rapidly spinning neutron star, a city-sized object containing the mass of our sun. As the stellar remnant rotates, it sends a powerful radio beam sweeping across space. Whenever that beam hits our line of sight, we receive a precise tick or pulse, ultimately proving the existence of these extreme, highly dense stellar remnants.
Project Ozma, led by Frank Drake, was the foundational moment for SETI, shifting us from passive listening to active search. The logic was simple. Tune in to the 1420 MHz frequency of hydrogen, which Drake called the universal water cooler. He targeted two sun-like stars, Tau Ceti and Epsilon Eridani, listening for 150 hours. While no signals were detected, this effort marked a crucial legacy. We stopped just hearing the universe's static and started actively listening for a structured message.
The timeline of radio astronomy illustrates how quickly we began deciphering the invisible universe. Carl Jansky's initial 1932 discovery of the Milky Way radiation paved the way for Grote Reber's first detailed radio maps. By the mid-60s, the pace was astonishing. Penzias and Wilson's 1964 detection of the cosmic microwave background provided powerful evidence for the Big Bang, followed immediately by Jocelyn Bell Burnell's groundbreaking discovery of the first pulsars in 1967.
We have achieved an incredible evolution in radio astronomy, moving from single backyard dishes to global interferometry arrays. By linking telescopes worldwide, we create a virtual lens the size of our entire planet. This breakthrough means we no longer just listen to the static. We can now actively image structures like the event horizons of black holes, as shown here with M87, and successfully map the complex magnetic fields of distant galaxies.
Many people believe space is silent, but the universe is actually roaring with energy. We hear the echoes of creation, colliding galaxies and spinning neutron stars generating powerful signals. Carl Jansky initially thought that steady hiss was just interference, but it was the cosmos speaking directly to us. Our challenge was simply to build the necessary instruments, the ears, to finally capture this magnificent, invisible voice.
When classical astronomy was constrained by visible light, we saw only the thermal surfaces of stars, like the stellar dots in Figure 1. Radio astronomy radically revolutionized this view by penetrating the cosmic dust and mapping non-thermal processes, particularly the 21-centimeter emission from neutral hydrogen. This massive shift, Figure 2, unveils the true invisible structures of the galaxy, proving that the cosmic vacuum is not empty space, but a dynamic landscape humming with energy. The field of radio astronomy began purely by accident when Carl Jansky, investigating static for Bell Labs, found a steady hiss that peaked 4 minutes earlier each day. This specific timing, aligning with sidereal time, revealed the source was cosmic, Sagittarius A, the center of the Milky Way. This serendipitous realization in 1933 inspired Grote Reber to build the first parabolic radio telescope 4 years later, dedicating it entirely to sky mapping and confirming the galaxy itself is a radio emitter.
The expansion of the universe acts as our cosmic time machine. Light emitted in the hot, dense past is stretched out by the increasing scale factor as it travels to us in the present. This stretching is measured by redshift, Z, where high Z values mean we are looking farther back in time. Critically, the photons emitted when the universe was just 3000 Kelvin experienced such an extreme redshift, Z equals 1100, that we now observe them as the cosmic microwave background radiation.
In 1964, Arno Penzias and Robert Wilson detected a persistent, annoying noise in their new horn antenna, measured at 3.5 Kelvin. They tried everything to eliminate it, even meticulously removing what they termed white dielectric material, pigeon droppings, from the equipment. The noise persisted, remaining constant and isotropic. What they had stumbled upon was not interference, but the cosmic microwave background, the residual radiation from 380,000 years after the Big Bang itself, strongly confirming that the early universe was much hotter and denser.
Observe the perfect black body spectrum of the cosmic microwave background, measured precisely at 2.725 Kelvin. The high-precision data from the COBE-FIRAS experiment aligns flawlessly with Planck's law, definitively proving the early universe was once in thermal equilibrium. This emission originated in a hot, dense plasma, and its release marks the critical transition between that radiation-dominated state and the ensuing cosmological dark ages, just before the formation of the first stars. The cosmic microwave background isn't a static background. It acts as a universal reference frame for absolute motion in the cosmos. The prominent dipole pattern you see, the distinct hot and cold spots, is caused directly by the Doppler effect. This reveals that our solar system is speeding through this ancient afterglow at an impressive 369 kilometers per second relative to the CMB, heading toward the constellation Leo. This velocity defines the true cosmological rest frame. The cosmic microwave background is incredibly uniform, varying by only 1 part in 100,000. But mapping these fluctuations reveals serious anomalies at large scales. Notice the unexplained cold spot and the infamous axis of evil, a linear alignment across the sky. These features are highly significant. They suggest either systematic measurement errors or strong evidence for new physics regarding the early universe's geometry, fundamentally challenging the standard model we rely on today.
Back in 1967, Jocelyn Bell Burnell detected an unusual 1.33-second periodic signal, initially labeled Little Green Men. We now understand the mechanism. These are rapidly rotating neutron stars whose strong magnetic fields accelerate electrons. These particles emit focused beams of synchrotron radiation. Just like a cosmic lighthouse, we only register an observed pulse here on Earth when that intense beam sweeps directly across our detection path.
Interstellar space functions like a plasma prism. It contains free electrons that slow down radio waves based on their frequency. As the graph illustrates, high-frequency pulsar signals arrive faster than their low-frequency counterparts. This measurable time difference is called the dispersion measure, or DM. Crucially, this delay allows us to calculate the distance to the source star, essentially using the intervening electron column as a highly precise cosmic odometer.
Pulsars are incredible cosmic clocks used to test the very fabric of spacetime.
General relativity predicts that binary systems, like the Hulse-Taylor pulsar shown here, must lose energy by emitting gravitational waves, causing orbital decay. The resulting observation matched Einstein's math exactly, earning a 1993 Nobel Prize. Now, we leverage these precise stars as pulsar timing arrays, essentially creating a massive, galactic-scale detector for gravitational waves across the universe.
Fast radio bursts are one of the greatest mysteries in astronomy, defined as millisecond-long, brilliant radio blasts originating billions of light-years away, fundamentally distinct from the regular pulses of a pulsar. The discovery of repeaters, like FRB 121102, is key because it rules out simple catastrophic collisions, suggesting a repeating cosmic engine is at work. Current theories overwhelmingly point toward highly magnetized neutron stars, or magnetars, but these powerful extragalactic signals could easily represent entirely new high-energy physics.
While most main sequence stars are radio quiet, certain red dwarfs, like Proxima Centauri, regularly flare violently. This radiation is generated by the electron-cyclotron maser mechanism, where plasma is channeled along magnetic field lines, causing massive radio outbursts. Understanding these sudden stellar events is vital. These flares significantly affect the space weather around neighboring exoplanets, forcing us to reevaluate our long-term predictions for their habitability.
In 1974, we broadcasted the Arecibo message, a profound 1,679-bit greeting aimed at the distant globular cluster M13, 25,000 light-years away. This iconic signal details our fundamental building blocks, our elements, our DNA structure, and a representation of the human form, along with the technology used to send it. Although the target will have shifted when it arrives, this message remains a powerful demonstration of human achievement and our enduring, ambitious attempt to initiate a dialogue with the cosmos.
The inverse square law is the defining barrier to interstellar communication. As our radio signals propagate spherically, their intensity drops exponentially, meaning our human radiosphere dissolves into background noise within just a few light-years. Detecting our old TV broadcasts even 100 parsecs away requires an astronomically sensitive receiver. This physical limitation means that unless humanity specifically directs a powerful beam toward a star, we are, to the rest of the cosmos, effectively invisible.
Our observable horizon stretches back 13.8 billion years, beginning with the Big Bang in the CMB. After the initial light, we enter the crucial Dark Ages, a period we hope to illuminate using the faint 21-centimeter hydrogen line before the first stars and galaxies formed. Understanding this vast cosmic timeline reminds us that every signal we receive, from ancient pulsars to modern FRBs, is fundamentally a message from the past. We are operating in a universe defined by the speed of light, and we are just beginning the monumental task of decoding the static.
We start our investigation in 1936 Berlin, where a powerful 40-kilowatt Olympic broadcast signal was launched on the 180 megahertz frequency. This signal gave rise to a powerful pop culture myth that the broadcast somehow returned years later as an echo from space. Today, we will separate that myth from scientific reality, connecting the physics of that initial transmission directly to Carl Jansky's foundational work on galactic radio emissions, revealing the true cosmic origins of those unexpected sounds.
We begin our summary with the foundational discoveries of early radio astronomy. In 1927, scientists first noted unexplained 3-second-long delayed echoes. 5 years later, Carl Jansky achieved the critical detection of star noise emanating directly from the center of the Milky Way. This validated that cosmic radio sources existed. While the notorious 1936 Hitler broadcast has now traveled 88 light-years away, these pioneering efforts quickly culminated in Grote Reber building the first dedicated radio telescope in 1937 to map the celestial radio sky.
Our first deep dive takes us to the 1936 Berlin Olympics, the first live televised sporting event in history. This original broadcast, which opened with the declaration, "I call the youth of the world,"
was transmitted using high-frequency radio waves specifically designed to penetrate the ionosphere. As Carl Sagan popularized In Contact, this landmark moment created a powerful cultural myth, the idea that this high-power signal was the initial human attempt to wake up the galaxy and initiate our story with the cosmos.
The core challenge to receiving an answer lies in the physics of signal return. Radio energy expands spherically, meaning that doubling the distance reduces the signal strength by a factor of 4. Our earliest broadcasts, like the 1936 signal, are now incredibly weak. As the analogy shows, receiving this signal at 100 light-years is like detecting a single snowflake against all cosmic background noise. Without active, fictional amplification, that initial energy is already indistinguishable from the background.
We often imagine our signals flooding the galaxy, but let's check the reality. Our current radio bubble, representing the furthest reach of our oldest, strongest broadcasts from the 1930s, is only about 90 light-years out. In the context of the Milky Way, which is 100,000 light-years across, this sphere is incredibly tiny. Our signal hasn't even left our immediate stellar neighborhood. Simply put, to the overwhelming majority of the galaxy, planet Earth remains completely silent.
Case file number 2 explores the 1927 phenomenon, the signal that did return. A standard radio transmission from Eindhoven received a primary echo, but 3 seconds later an anomaly arrived, a second, highly delayed echo. Jürgen Hals noted that this 3-second lag proved the signal had traveled an astonishing 900,000 kilometers, far past the orbit of the Moon, and then bounced back, suggesting unusual atmospheric reflections from plasma clouds or ionospheric ducts. Our third case file highlights Carl Jansky, the Bell Telephone Laboratories engineer tasked in 1932 with eliminating static interference for transatlantic voice transmissions in Holmdel, New Jersey. Jansky's objective was purely commercial, but the result was revolutionary. Instead of solving a phone issue, he discovered a persistent, mysterious hissing sound that he traced directly to the Milky Way center. This star noise was the first radio signal captured from space, marking the accidental birth of radio astronomy.
This is Carl Jansky's famous merry-go-round antenna, built using simple materials like Model T Ford wheels to rotate the Bruce array every 20 minutes. Jansky's initial goal was to locate sources of terrestrial radio static. He successfully categorized local crashes and distant rumbles from thunderstorms. However, his work revealed a third, persistent signal, a steady hiss static of entirely unknown origin. That unidentified third sound is exactly what pointed us toward the cosmos.
The breakthrough came when we analyzed the precise timing of the peaks, finding the signal repeated exactly every 23 hours and 56 minutes. This periodicity wasn't a solar day, it was the sidereal day, Earth's rotation relative to distant stars. Because the signal peaked exactly 4 minutes earlier each day, we knew the source had to be fixed in space, not in our solar system. This crucial data definitively pinpointed the origin of the star noise far away in the constellation Sagittarius, right at the galactic center.
Meet Grote Reber, the amateur radio operator who became the world's first intentional radio astronomer. In 1937, he built this incredible 31-foot parabolic dish right in his Illinois backyard. This monumental, self-funded effort truly launched the field. For nearly 10 years, Reber was the only radio astronomer working globally, and his perseverance led directly to the creation of the first detailed radio map of the entire night sky, setting the stage for modern astrophysics.
When we first tried to map the sky, we assumed the static was purely thermal, which led early attempts like Reber's at 3300 MHz to fail completely. The true breakthrough arrived when attention shifted to much lower frequencies, around 160 MHz, revealing the signal followed a non-thermal curve. This definitively proved that the cosmic static originated from synchrotron radiation, highly energetic electrons spiraling in the galaxy's magnetic fields.
The Little Green Men incident began in 1967 when Jocelyn Bell Burnell detected this incredibly precise radio signal repeating every 1.337 seconds. Because of its perfect, seemingly artificial rhythm, it was jokingly labeled LGM-1, suggesting alien origins. While the team briefly considered the exciting possibility of communication, the reality proved even more groundbreaking. This signal was the first observation of a pulsar, a rapidly rotating, highly magnetized neutron star.
In 1960, Frank Drake initiated Project Ozma, fundamentally shifting the focus of astronomy from passive cosmic noise to actively searching for intelligent information. He targeted two nearby sun-like stars, Tau Ceti and Epsilon Eridani. The team listened intently to the 1420 MHz frequency, the hydrogen line, which was considered the universal water cooler for civilizations to communicate. Although Ozma was a seminal moment for SETI, the result was famously anticlimactic: complete silence, save for one brief false alarm from a passing aircraft.
The journey from accidental echoes to directed searching happened remarkably fast. Starting in the late 1920s with LDEs, the 1932 discovery of the hiss immediately revealed the cosmos was radio loud, spurring the invention of the first parabolic radio telescope. After we successfully bounced radar off the moon in 1946, all that foundational work paved the way for Project Ozma in 1960, our first organized attempt to actively listen for intelligent extraterrestrial signals.
The 1936 broadcast, the artifact of our earliest strong signals, is now a silent shell 180 light-years across, racing perpetually outward. While we won't hear our own history echo back, pioneers like Jansky and Reber proved the sky is not silent. In fact, the universe is roaring with the incredible physics of creation, waiting constantly for us to tune in and decode its true signals. In 1936, the first high-power television signal left Earth from Berlin, beginning a decades-long journey into the void. Popular culture suggests this signal was received and returned by extraterrestrials, creating an enduring myth. Today, we conduct an interstellar investigation, analyzing the true physics behind that historic broadcast, determining its actual destination, and separating the fascinating science from the long-held science fiction surrounding humanity's initial electronic handshake with the cosmos.
The intriguing premise from Contact suggests the 1936 Olympic broadcast was captured by advanced aliens and bounced back to Earth. However, the physics reality is far less dramatic. That original signal is now a sphere 180 light-years across, utterly decayed into unintelligible static, indistinguishable from background noise. Radio waves simply travel outward forever unless intentionally reflected, and even back in 1936, the earliest cosmic listener Milky Way, not Berlin.
Let's dive into our source event, the 1936 Berlin Olympics. This entire spectacle was a masterful technical flex and a calculated act of Nazi propaganda intended to showcase the new Germany. While Hitler spoke of a sportive battle, the real intent was masking the regime's ideology. Critically, this was the first major televised event, utilizing high-frequency radio waves that could penetrate the ionosphere, proving the power of this new communications technology. The physics behind this escape hinges on the ionosphere, which naturally acts as an atmospheric barrier. While low-frequency AM radio waves are reflected and trapped by this layer, the high-frequency waves, specifically the powerful 1936 TV signal broadcast from Berlin, achieved a clean breach. Once past the ionized layer, the signal escaped into the cosmos on a perfectly straight trajectory. Traveling relentlessly at the speed of light, 186,000 miles per second, that historic broadcast is still moving away from us forever. The defining return scenario stems from Carl Sagan's novel, Contact. As visualized here, the original broadcast traveled 25 light-years to Vega, was captured, and then mirrored back to Earth in the 1990s. Sagan designed this plot device to create a stark contrast: the profound, unifying nature of the alien response against the trivial and violent content of our initial transmission.
Ultimately, this scenario acts as a powerful mirror, compelling us to confront our very first message to the cosmos.
The inverse square law dictates why our broadcasts fade so quickly. As radio wave energy expands spherically, its intensity is inversely proportional to the square of the distance traveled. To put this in perspective, the infamous 1936 broadcast was already buried beneath cosmic background noise by the time it reached the nearest star. To resolve that faint signal today, any alien civilization would require an antenna array comparable in size to our entire solar system. Let's zoom out and put our search into perspective. Despite nearly 90 years of expansion, our collective radio signals, that bubble of human noise, has only reached about 100 light-years from Earth. As you can see, compared to the 100,000 light-year span of the Milky Way, our radio footprint is microscopically small. Imagine throwing 100 darts at the galaxy. There's a near certainty none would hit our little blue bubble.
Moving beyond speculation, let's examine long-delayed echoes. This is a confirmed phenomenon, discovered in 1927, where radio signals return to the sender seconds after transmission. As the illustration shows, this occurs when signals are temporarily trapped in the magnetosphere or bounce off distant plasma clouds. The critical difference is that these echoes are delayed by seconds, confirming there is no known natural mirror in deep space capable of reflecting a signal back after decades.
In the 1930s, while the world was focused on political unrest, the real listeners were looking up. Carl Jansky accidentally found cosmic static that peaked every 23 hours and 56 minutes, realizing he was hearing the Milky Way. A few years later, Grote Reber built the first dedicated radio telescope in his Illinois backyard and meticulously mapped the radio sky. The incredible irony is that these pioneers, discovering the universe's most powerful sources, were the only humans truly ignoring Earth entirely.
Back in 1967, astronomers detected an incredibly precise radio signal repeating exactly every 1.33 seconds. This stunning regularity led them to jokingly nickname the source Little Green Men 1. However, the explanation was far stranger than extraterrestrials. The signal originated from a pulsar, a rapidly rotating neutron star. The lesson here is crucial. The universe is inherently full of precise, rhythmic natural phenomena that can easily mimic signs of intelligence.
Arno Penzias and Robert Wilson spent months trying to eliminate a persistent excess noise from this antenna in 1965. After ruling out every local source, from urban interference to cleaning out the pigeon droppings, they realized the static wasn't terrestrial. This noise was the cosmic microwave background, the faint thermal remnant of the Big Bang. When we listen to the quietest parts of the sky, we are literally hearing the birth of the universe, not our own echoes. The difference between leakage, unintended, weak radio signals, like those from the 1936 Berlin Olympics, and a true message is crucial. The 1974 Arecibo broadcast was an intentional, high-power beam sent 25,000 light-years away to globular cluster M13. That incredible distance is the ultimate constraint. Since the signal takes 25,000 years to arrive, any potential reply wouldn't return for 50,000 years. Truly, interstellar conversation demands a multi-millennial commitment.
When we separate the dramatic narrative from the cold, hard facts of physics, the contrast is stark. The idea of an advanced Vega civilization capturing and retransmitting the signal with high fidelity is certainly compelling. Unfortunately, the signal is physically moving away forever, fading rapidly into static. Given the constraints of the inverse square law, we must conclude that even if it did return, it would simply be undetectable from Earth. Consider our electronic footprint. Since the 1936 broadcast, we became a radio-loud species, announcing our presence for a mere century, a blink of an eye in cosmic time. Our transmissions, radiating outward, represent more than just physical energy. They are a cultural signal. This enduring and expanding legacy reminds us that every broadcast we make, whether propaganda or poetry, becomes part of humanity's permanent mark on the universe.